Okay, so I'm recording, everything's right with the world. Last day of May, you had homework 10 due. We're finishing lab 5 this week, and it will be due next week. From lab today, I know Vinod was saying that a lot of people didn't finish part 1 of lab 5 last week. Part 2 of lab 5 is really short, so that can help you catch up. And lab 5 is due next week. Exam 2 is Wednesday, April 7th in Frankie 436, unless you've made an appointment with me to take it on Tuesday. What else do we have going on? Oh, after homework 11, there's only one more lab due, lab 6, and there's only one more homework, and that will be on BJTs. What we get to spend 3 whole days on. Which is amazing. Now, oh yeah, I'll get to that. I have a slide for that. This is last decade's technology. This is what you're seeing in Cedra Smith. It still gives you all the information and models that you need to get to today's transistors, because they basically function the same way. Modern transistors look more like FinFETs. This is last year's MOS technology. I just raise the source and drain and wrap the gate around it, and they become more ideal MOSFETs, better MOSFETs. These nanowires are like the 3-6 months ago technology. They decided they had to make them a little bit wider to get more current through them, and they call them nano sheets. And if you really want to know more about processing technology and where things are heading, I really highly recommend this lecture that I posted in BB Learn. It was my 380 class yesterday, and this is Dr. Cambeau, and Bertrand Cambeau is probably one of the most knowledgeable people anywhere on MOSFET technology. He was a Silicon Valley, he was on the board of several Silicon Valley companies, and now he's a professor at NAU. And just, and he's going to be my advisor, graduate advisor next year. Just listening to him talk, you'll understand kind of what the state of today's technology is. And this is probably the largest industry in Arizona, especially, it's definitely the largest industry for electrical engineers, is semiconductor fab and design. So if you want to learn more about that, the video is posted to BB Learn for you guys. And it's in your class video section, and it's labeled Dr. Cambeau, EE280 Dr. Cambeau. It's not on my public YouTube channel. You can only get to it with the link, but it's still YouTube. Who was that? Okay, I don't know who that was. Nobody knew that I see. Okay, so we're going to wrap up MOS analog.
That was me, sorry.
What?
Jordy.
Jordy.
I'm so sorry.
Yeah, that's all right. So we're going to wrap up MOS analog today. You were one of the people that was missing, so that makes it much easier. And we'll have the exam review on the next class, which is on Monday. Really have 2 problems to work through today. It's one of those days. Yes, 2 examples. One of them is a lot like your last homework problem on homework 11. Which is the entire amplifier design, and that is actually, oh, should I tell you guys? If you look at the exam review slides and the exam review solution, the last problem on homework 11 is solved in the exam review. Okay, so this is what we want to do. We want to design an amplifier, and we want to develop a generic process that will work for any amplifier I choose, whether I have an RD here or I have some other resistor network here. Maybe I've got capacitors in there. Maybe I have a resistor here. Maybe I have a couple of resistors on the gate. We want to be able to figure out how to solve this despite everything that's going on. So it's kind of like superposition. We're going to divide the DC circuit from the AC circuit, solve each one of them separately. there's information you need from the DC circuit to solve the AC circuit. So we'll do that one first. So our first step is the bias point calculation. It's also called the DC analysis, the DC bias point, or the Q point. To get there, we're going to have to draw the DC circuit. We'll have a set of rules for that. And we determine the three big things we need to know are ID, VGS, and VDS, all capped letters, so those are DC values. And we can use these DC values to calculate the small signal parameters, GM and RO. And the GM and RO are kind of our basic assumption on this is our signal is so small that it's not going to disturb the value of GM and RO. We'll treat them like a constant. We'll talk about how the transistor model we're going to use, the small signal transistor. That'll be the first part of this lecture. Once we get in, we figured out what GM and RO is, we can put them in the AC circuit, and we can draw that AC circuit and use it to calculate the voltage gain. It's nothing more complicated than a voltage divider and Ohm's law. And there's a weird passive sign convention thing going on in here. When we get to the BJT section, we'll talk about amplifiers with BJTs, and this general method applies to both BJTs and MOSFETs, and we will do more of this in EE280. This is the whole EE280 is digital circuits with MOSFETs and analog circuits with MOSFETs. So the first thing, we're going to try to build a model. We're going to take how the transistor behaves, and we're going to create a circuit model that we're going to use that's kind of a shorthand for all these effects inside the transistor. The first thing we have to do is we're going to calculate the voltage gain. That's the goal. If we look at the ID VGS equation, we're assuming it's in saturation. If it's going to work like an amplifier, it will be in saturation. And the gate current is always going to be 0. So if we take the derivative of ID with respect to VGS, this is just a simple quadratic. You can multiply it out if you don't remember the quadratic rule. But this is going to come out, you get a 2 inside there, and the 2 cancels out this 2, and you get this Kn VGS minus VT. So this is a change in ID with respect to VGS. Here's my model. It's a 3-terminal device. We're going to start filling it in. I need to know what VGS is. And a change in ID with respect to VGS is going to be a dependent current source. So I'm going to put this dependent current source in here that will model a current going between the drain and the source. It's going to depend on VGS, and I'm going to make up some name of a constant and stick this out in front that relates the two, and I'm going to call that GM. So this will equal GM times VGS. This is the simplest model of a transistor that you can get. If I try to take the derivative of IG with respect to VGS, IG 0, so that ends up being 0. This model has no gate current because there's no path for current to flow. The IG will necessarily have to equal 0. It's actually really small. We measure it and we use it to make encryption keys. Of course we do. In the lab. But this is this is the small signal model, as basic as I can get. I increase VGS, I get an increase in ID. So when I look at we want to figure out, we put that parameter in there, we called it GM. We want to figure out how to calculate GM based upon our current equations. We know saturation current equation looks like this. We know that Kn is our Kn prime times W over L for a transistor. When I do this and I try to find, when I calculate the change in ID with respect to VGS, for this particular type of transistor, a MOSFET, what I get is I get Kn VGS minus VT. It's just the derivative of this. Another expression for VGS minus VT is V over voltage, so I could replace that in there. I could manipulate these equations and come up with a term that doesn't depend upon Kn, and that would be 2ID over V over voltage. And I could also go through and do one that doesn't do the same kind of algebraic manipulations and come up with one that doesn't have V over voltage in it. Square root of 2 Kn ID. You can use either one of those 4 equations to calculate GM, and they should come out the same. They've come out the same every time I've done it, all 4 ways. But depending upon the information you have in the problem, one of them may be simpler to calculate than the other. If you know V over voltage and Kn, use this one. If you know ID and V over voltage, you use the second one. Just use what you have and write them all down on your note sheet, because you never know what information I'm going to give you. I've just literally had so many times people have gone through exams and say, I can't calculate this. And look, here's the equation for GM. And I go, no, you didn't write them all down. So the next effect that we want to put in here, we've already got the current source. And the current source is, it's an IDS, so it's going in this direction. GM, VGS. The next thing we're going to put in our model, instead of modeling the channel length modulation like this, I want to model it with a circuit parameter, an actual circuit device. It's not a real resistor, but it's going to be put in this model to replace the effect of 1 plus lambda VDS on this equation. The total drain current equals what we typically calculate for ID, which is what's circled in orange there, times the channel length modulation parameter 1 plus lambda VDS. If I take the derivative of ID with respect to VDS, this is the only thing that changes in here, is this last part. I get my old ID, the Kn prime over 2W over L VOV squared, times lambda, because this will reduce. So a change in ID with respect to VDS looks like a resistor between that ID is flowing through and that VDS is across. And we call this resistor little RO. So you want to calculate little RO, it's just 1 over lambda ID. Now, I can either use the equations to calculate the current like this, or I can use the circuit model to model it. You don't want to do it twice. And when you calculate RO, you don't include the channel length modulation. It's just the orange part of the equation. Really common mistake, and yes, I do it occasionally too. So this is our model of our transistor. We've got 3 terminals, gate, drain, and source. As simple as it can get. The SPICE model also has about a dozen capacitors in it, probably another half a dozen resistors, and other weird effects. It's about a page long, double spaced, of just parameter names. Developed at Berkeley, and the whole world uses it. Now, I said when we do these, what we're going to do is we're going to analyze a DC circuit and we're going to analyze an AC circuit. So one of the key skills you need to get, and I've put this on almost, I put this on the 380 exam last week, is you have to be able to draw the DC circuit. Now, you can simplify the circuit a good bit because the capacitors at DC are open circuits. So any place you see a capacitor in there, and this will be an example 2, but not example 1, you just open it up and you ignore everything on the other side of the capacitor. Then I'm going to deactivate and I just wrote this slide today, so it's not in the actual slides. You're going to deactivate the AC sources, but I write it down every semester. So, and the way you deactivate a source is voltage sources go to shorts. They just become a wire. And AC current sources are going to become opens. And we'll do a few examples with this too. Now for the AC circuits, we're not going to be thinking about what the frequency response is. We're just going to say the capacitors are big enough and the frequency is large enough that we're going to treat the capacitors like they're short circuits. So we're going to replace them with a wire. There's no 1/j omega c here. We're simplifying this for hand calculations. And then we want to deactivate the DC sources. Deactivating sources follows the same rules. The DC voltage sources are going to be shorts. So if I have a connection like this to VDD, we could think of that as being equivalent to having this node tied to a voltage source of VDD to ground. So pretty much my VDD, when I draw these, I just replace VDD with ground. Yay. We've got all my DC sources go away. All my DC current sources are going to be open circuits. So they will just get cut out of the circuit. And then the final step is to replace the transistor with the small signal model, the gate, the source, and the drain with the dependent current source and RO. That's as much as we're going to do for hand calculations, and it will get you in the ballpark of how these circuits work, and it'll give you an intuitive feel for how they work. So when you're actually analyzing them with something like Multisim or with Mentor Graphics or Cadence or another professional grade tool, you can actually understand the results you're getting. Okay, so let's start out with a really basic circuit. The DC circuit, our first step is, well, we have no capacitors. We want to draw the DC circuit. I'm going to deactivate the AC sources. There's only one AC source in here, and it's little v, little g, little s. So I basically, all I do is I deactivate it. I replace it with a wire. It's gone away. There's the equivalent circuit, the DC equivalent circuit. Now we want to draw the AC model. So that's the DC model. You guys got that? I'm going to give you a minute to absorb it. Let's just draw let's draw the AC model over here. So for the AC model, I have the transistor. My source is still grounded. My output sees RD, but RD was connected to a DC source, VDD. I deactivate that. It goes to ground. And I still have this little VDS stub sitting out here. My gate saw an AC source and a DC source. I leave the AC source in, and I short out the DC source. So that is the AC circuit, and I knew I should have known. And then the final step is to replace this with my model, small signal model. So my small signal model looked like this. There's a gate, there's a little v, little g, little s. There's a source down here. There's a drain up here. There is a current source. We haven't calculated GM, so I'm just going to leave it as GM. GM VGS, and there's a little RO, and we're going to figure out what I need to hook everywhere. If I look at the source of this transistor, it's tied directly to ground. So in the model, I'm going to tie the source to ground. The drain sees a resistor to ground. So I have to put a resistor RD to ground right there. And my gate sees an AC source. And they're both named the same thing, but I'm okay with that because little VG, both of them equal the same thing. The voltage across GS is going to equal the voltage of the source. And that's a circuit. It looks complicated, but when we divide and conquer that circuit, it's actually just a combination of, worst case, it is a voltage divider and an application of Ohm's law to solve that one. Okay, we'll have better pictures of it later. So, and this is example number 1. Told you we get through 2 examples today. We're going to do the DC analysis. There's no caps. The only thing I have to do is deactivate that AC source. So this is going to go away. It's shorted out. We're given BDD as 1.8 volts. We're given ID is 250 microamps. We're given the threshold voltage and Kn. We want to find big V, big G, big S. And the way I'm going to get there is I'm going to take this ID equation and I'm going to solve it for VGS. Since it's in saturation, if you know ID, you know VGS. I get 2 ID, and then on the bottom, I'm going to get Kn prime W over L. And then I would have to take the square root of that and add VT to it, and I get VGS. That's just algebra. So I can plug in all the numbers I'm given. I've got 0.4, yeah, of course not, plus the square root of 2 times 250 micro. Kn, I don't have Kn prime, but Kn equals Kn prime W over L. So I can plug that in. I've got 5 milli. And when I take the square root, I'm always going to take the positive square root. Unless I'm using PMOS, then I always take the negative square root. Sorry. That's why we don't do PMOS in here. This is part 2, number 4. I'm just looking up the answer. That comes out to be 0.716 volts. Okay, so we've got VGS. Now we have to keep the transistor in saturation. And we have this equation right here. So if VDS has to be greater than or equal to VGS minus VT to keep it in saturation, we've got VGS now. So it has to be greater than 0.716 minus 0.4. I have to keep VDS greater than or equal to 0.316 volts. Okay, this is the tricky part. This is the thing we get. Okay. This is the thing that kills you on 380. So the next thing I want to do is I want to choose RD for maximal symmetrical signal swing. Now, if I think about, and I don't want to do it over there. If I think about this graphically, my minimum, this is VDS, my minimum value of VDS is going to be 0.316. And the highest value I could get, if my AC plus my DC value of the current added up to be 0, the highest voltage I could get here would be 1.8 volts. Would be my power supply voltage. So I know my signal is going to swing between 0.316 and 1.8. If I want to get the biggest AC signal possible, I put my VDS right in the middle of those two. And then when the signal swings low, it goes down to Vmin. When it swings high, it goes up to Vmax. And we want to have the biggest value possible. So we have to put VDS at the midpoint of 1.8 and 0.316. So we're going to choose VDS. No, thank goodness. Okay, in the middle. And the way I find a midpoint, you may have a different formula, but any midpoint formula works, is I take 1.8 minus 0.316, and I divide the difference by 2, and then add 0.316 to it. Add the minimum value. And that comes out to be number 4. Next page. 1.05 volts. Yes. This is the VDS I want to use. Now the thing that's going to set VDS is this resistor. So now I'm going to use Ohm's law to calculate the resistance value. That wasn't given. So the voltage drop across RD is VDD minus VDS, 1.8 minus 1.05. That has to equal the current through the resistor, which is 250 microamps, times R. And we can use that to solve for R. What the heck is R? I should have flipped the page. It's 2.99 k ohms. Now, if you go to your parts cabinet, you're only going to have limited numbers of resistor values. You probably have to go to like a 3 k ohm. That's as close as you can get, or whatever. I think it's 3.1 is the standard value. So you get it as close as you can. Okay. And we've done the DC analysis on this circuit. So we've got our ID. Remember what we were shooting for was to calculate, let's use red. Let's use something dramatic. Red. The 3 things we wanted to calculate on our DC operating point were ID, which was given, VGS, we calculated right here, and VDS, which is right here. We could use those to calculate our small signal parameters, and I hope that's the next slide.
Real quick.
Yes.
On the last slide, the numbers you used to calculate in the Ohm's law, that's VDD minus VDS?
Yes.
Okay.
Yeah, it's the voltage drop across the resistor equals IR.
Okay.
It's not really V equals IR because V is always a difference. It's like a potential energy difference. It's kind of like energy. Okay. That's an amazing point because I still see people missing that in 380 and 490. Shh. Okay, so we got all the values. We now want to calculate. Thank you. We now want to calculate GM and RO. So GM, what do we have? What was given? What did I use? GM, I used this first one because I had all the information. So KN, if I go back to the previous slide, it was given, it was 5 milliamps per volt squared. So 5 milliamps per volt squared times something that's VGS was 0.716 and VT was 0.4, I believe. Yes. And that has units of volts. So when I multiply milliamps per volt squared times milliamps per volt squared times volts, I'm going to get an answer that's in like milliamps per volt. And this is GM number 5. It's 1.58 milliamps per volt. And we know that V equals IR. So the units of resistance are really volts per amp equals an ohm. So we could say, let's say this looks like 1 over ohms and call it millimoles too. Upside down ohm. And it's really kind of like that because looking into that source, when you use the Thevenin equivalent of it, you see a resistor of 1 over GM when we get to that part of 380. So let's go to another weird color. We want to calculate RO. Now we were given lambda.
I have a question real quick.
Okay, good.
When you did the, when you saw for GM, I thought that KN from the last slide was KN multiplied by W divided by L. I thought you
Yes.
switch. But why do you use, since they're included variables with that KN, how come you're still allowed to use KN by itself for the same value?
Okay, so this is KN prime.
Oh,
W over L.
okay.
And
Yeah,
KN prime is different from KN.
okay.
Wait till we get to 380. Oh, that's what we're hitting in 380 now. There's RN, there's RN prime, there's RL, there's RL prime. Those little dashes mean a lot. Okay. But anyways, 0.02 is what the number we were given, and ID was, what was it, 250 micro? Yes. 250 micro. And this should come out to be in like kilo ohms if all's rational with the world. And yes, it is 200 kilo ohms. Okay, so we've got GM and RO. You put all this on one slide? Yes, you did. Okay. So the next thing we want to do, we can put in our model. We've got a gate, we've got a drain, we've got a source, we've got a little b, little gs. Great, thank you. Can you see that? Yes, you can. My GM is a number now. It's 5 milli times whatever VGS is. And my RO is a number 2. It's 200K. I'm trying to make this small. Now we want to look at how we hooked up the circuit. So I'll put that in a different color. As we hooked up the circuit here, the source is grounded. So I'm going to ground the source. On my AC circuit, I have to deactivate VDD, so that goes to ground. So I see RD to ground. And on the gate, I really want to draw this better. We see VGS. So pretty much on the input side, I can say that VGS equals VGS. That's not too complicated. This circuit on the output, let's just draw this a little bit better. Or, okay, so this, let's see if I can get to this. We have a 200 k ohm resistor to ground. These are connected to ground and these are connected to ground. So these are connected together. So what I'm really seeing here is I see this dependent current source, and I'm not going to try to fill in the numbers on this one. I see little RO, and I see RD. And this is my V out. Passive sign convention. You know, I get to say that at least once. My V out, since that's my output terminal, I have to define that as being positive and this being negative. Current is flowing into the negative terminal. That defies passive sign convention. So this current, the voltage it's going to produce at this output is going to be a negative number. And what I really have here is I have this current source. My output, V out, is going to equal the current flowing into it. It's going to be negative because of that violation, times the resistance. So my V out equals the current flowing into it is GM VGS. The resistance that that current source sees is the parallel combination of RO and RD. We want to calculate the gain. The gain's V out over VN, which in this case is V out over VGS. So the gain is going to be V out over VGS. It just cancels out, and I get minus GM RO parallel little RD. As we say in 380, GM big RO. We've got numbers for all this. We can plug it in. Our GM was, we've got to leave that minus sign in there. 5 milli. My RO we calculated was 200 K, and my RD was 2.99 K. So that parallel combination is going to be a little less than 2.99 K. Did I actually calculate it? No. But when I throw all those numbers in and calculate it, I get my gain is minus 4.67. And that, it's dimensionless, but I usually throw the units in volts per volt. I've done enough power amplifier design that I want to make sure I know what that is. So that's pretty much it. You get to do one of these problems on the homework, but it's a little bit more complicated. We're going to do a little bit more complicated problem next. And we literally have 3 slides for the next half hour. I think this is going to involve paper. Okay. Let's do this in my order. The first step is always the DC analysis. So I'm going to draw the DC circuit and analyze it. Now, first thing is my caps become opens. And so if this is an open circuit right here at C1, this whole part of the circuit just goes away. It's open. It's not going to affect anything. And this cap right here is also open. So I can get rid of all this stuff. This one's open also. It will help us later. We'll be thankful for it later. So I'm going to draw that. Basically, I've got the 4 resistors and the transistor and the power supply. I'm going to redraw this on bamboo paper to make this like a little bit more rational. Thank goodness. This is what, yeah, the timing diagram from 490. So what I had there, I have a picture in here. Yes, thank goodness. Okay, so I've got 12 volt, drawing too close to the edge. 12 volts to this resistor was 2.2 meg ohms. And I have another resistor down here, and I'm just recopying that circuit, 1.5 meg. And this is going into the gate of the transistor. The source sees another resistor. This is a variety of a common source, 12K. And we have another resistor up here. This is the DC circuit. It's also going to 12 volts, and its resistance was 22K. And we want to calculate, remember our goal is ID, VDS, and VGS. Was I given ID? Yes. My ID was given. It's 241 microamps. So that box is checked. Okay. To calculate VG, I have no current going into the gate, so I can use a voltage divider. So VG is just going to equal the 12 volts of the input times the resistance I want the voltage across, the 1.5 meg, over the sum of the two, 1.5 meg plus 2.2 meg. So VG looks pretty straightforward. It is 4.86 volts. Okay. We can use that ID equation. It's in saturation. We can solve the ID equation in saturation. It always looks the same. For VGS. VGS is the square root. I've done this enough. I've memorized it. 2ID Kn prime W over L plus VT. So we plug in the numbers we know there. 241 micro. I think I was given Kn. Yes, I was. It's whatever that was. 5 milliamps per volt or something like that. 5 milliamps. Plus VT. My VT is probably 0.4. No, my VT on this one was 1. And I get 1.98 volts. So we know this gate voltage here, it was at 4.86. We know the voltage drop between the gate and the source is 1.98. So my source voltage over here has got to be 1.98 volts less than my gate voltage. So this is basically, we know that VGS equals VG minus VS. We solve that for VS, we get VG equals VG minus VGS. That looks right. So this is 4.86 minus 1.98. We have VS. Okay, VS. What the heck is VS? it is 2.88 volts. Okay, so I've got VG and I've got VS. The only thing that's missing is VD. And this is Ohm's law. Ohm's law. So VDD, that point right there is VDS, the voltage between the drain. The voltage drop across the resistor has to equal its current times the resistor value. And we can solve, what are we solving for? We're solving for VDS. So VDS equals VDD minus IDRD. First time I taught this class, I had the students memorize it. And then I realized that they just used it blindly. It is just Ohm's law. Okay, and I'm still fighting that. VDD was 12. ID's 241 micro. RD's given 22K. We can get VDS. And what the heck is that? VDS is 3.82 volts. So we've gotten VDS, we've gotten VGS, and we were given ID. We're done with the DC analysis. That's enough to get us there. Okay, next step would be to calculate GM and RO. So this is the DC circuit part. This is what I called step one. Oh, great. What did I just do? This is what I called step one. Step one. Now we're going to move on to step 1B. 1B. Calculate GM and RO. So I'm going to use this formula, GN, GM, KN, VGS minus VT. So 5 milli, where's my VGS? It's right here. 1.98 volts. My VT was 1 volt. And I get 490 micromos. 90 microamps per volt. So there's my GM. And my little RO is 1 over lambda ID. Was I given lambda? Yes, I was given lambda is 0.02. You've got to be given lambda because once your transistor's built, someone's measured lambda or the early voltage. And ID was 241 micro, and this comes out to be 207 k ohms. 07 k ohms. So those are the two things we really need for the small signal circuit. 490 microamps per volt. I'm going to write this down. And 207 k ohms. Now we'll go back to the slides. No, you don't want the semiconductor physics slides. Oh, yeah, I did it anyways. Don't save. You don't want to see that. It'll scare you. Okay. We want to draw the AC circuit for this. Well, I'm going to erase all that. And we want to get the AC version of this. So for AC, my caps become shorts. These just get blocked out. And this becomes a short too. Since I've shorted out R4, I see a short to ground right there. A short in parallel with a resistor is a short. My DC sources, I only have one DC source, and that's this VDD. It gets eliminated, and it gets shorted to ground. Okay. That's what it looks like. Now let's redraw it in bamboo paper. Let's see what I got here. Can I split the screen? Can I make that small? Yeah, I can make that sort of small. And oh, then that goes away, doesn't it? Okay. I'm trying to figure out a way to get you guys to visualize this. I know what I'm doing, but that doesn't help you. So I have this circuit that looks like this. Let's just redraw it. I won't put any numbers in yet. That other resistor that was going up to the DC supply is also going to ground. So I'm just going to flip it over. There's the gate. Go back to the PowerPoint. So I had 1 k ohm going into the gate from the input source, and I have 1.5 meg to ground. This 2.2 meg is also tied to ground, and I'm just going to flip that one upside down is basically what I did. So this is 1K, this is VN, this is 1.5 meg, and this is 2.2 meg. Okay, off the source of that, I've shorted out the resistor with a cap. So this is just going to ground. Now on the drain, what I'm seeing 22K to ground, but I'm also seeing that in parallel with 100K to ground, because they're both tied to VDS on one side and they're both tied to ground on the other side. So I'm seeing those two in parallel. Seeing 100K in parallel with 22K going to ground. That is the AC circuit. Now I want to put in the small signal equivalent to this. So I start with the gate. We'll be done soon. Whatever you're thinking right now, we'll be done soon. At gate, drain, and source. I've got my dependent source. I've calculated GM. So my GM VGS is 400 micro times VGS. And then my RO I've calculated. It was 207K. Plus, minus. Okay, I got to change colors. Is that red? Yeah, okay, good. Now I'm going to look at this circuit, and I'm seeing this is my source. What is connected to the source on that circuit? It's connected to ground. So I'm going to connect my source to ground. Off of the drain, I see the parallel combination of two resistors, 100K. Was it really 100K? Yeah, it was. I got that right. In parallel with 22K. It's connected to ground, but this node's connected to ground. So all these are connected together. On the input, on the gate, I've got to connect the gate to this thing out here, VN. I see 1K ohm, and I see the parallel combination of 1.5 and 2.2 to ground. 1.5 meg in parallel with 2.2 meg to ground. That's connected into the gate. So there's my small signal circuit. This is where I really want to do the divide and conquer thing. What I'm going to do is I'm going to calculate VN in terms of VGS. And for that, I really have to move you guys. Oh, that is so, let's go blue. No, let's not go blue, let's go green. Okay, green. What I'm going to do here is I'm going to look at this as two separate circuits. I've got this front end, and I have this back end. Both of those are referenced to ground, so I can do that. It makes it a much simpler problem and much less ugly problem to solve. This front end right here, the gate circuit, we'll call this the gate circuit. Just looks like a voltage divider. So I could say VN, VGS, sorry. VGS is going to equal my VN times the voltage I want the output on is this one right here, 1.5 meg in parallel with 2.2 meg. Over the sum of the voltages, which is 1K plus 0.5 meg in parallel with 2.2 meg. So this is going to be a number, VGS over VN is going to be a number pretty close to 1. And I'm going to write it that way. You'll see why in a minute. VGS over VN equals that part. Okay. Did I calculate that? I hope so. VG, yeah, it's 0.999. This is why we use such big resistors in that at that gate circuit to get most of the voltage into that thing. Okay. Now we are going, I'm going to move you guys to the left for a minute. I'm going to go with red. I want a really bright red. Okay. Okay. And I'm going to move you guys back. Did I mute myself? No. Okay. Now we're going to look at this part of the circuit. So that part of the circuit just looks like a current source going into the parallel combination of two resistors. This is the voltage we want right there, my V out. So I could say V equals IR. I have a passive sign convention violation because current's going into the negative terminal, so I have to make this negative. So my I part of this is the current source is 400 micro times VGS. The R part of this is 207K in parallel with 100K in parallel with 22K. And the voltage that I'm measuring here is V out. So I could write another expression, V out over VGS. That will just be a number. I mean, it's kind of messy to calculate. I could do it as the reciprocal of the sum of the reciprocals, if you remember that. I could calculate probably what I could calculate 100K in parallel with 22K, product over sum, and then do product, take that result and do product over sum with 207K. Either way, it comes out to be 19.3K. So my V out over VGS is 400 micro times 19.3 K ohms, which is a number, and a much larger, it's larger than 1, negative 9.45 volts per volt. Now, what have I calculated here? We're almost done. I've calculated V out over VGS and VGS over VN. We're gonna go black. We're gonna just do something really dark here. Okay. If I take VGS over VN and I multiply that by V out over VGS, my VGS's cancel and I have V out over VN. This was what I was looking for. So my V out over VN is just going to be negative 9.45 times 0.999. And that is, no, it was 9, this was 9.46, sorry. This is 9.46 because it's the final answer that's negative 9.45. We're done. There's a homework problem like that. If you get stuck, look at the exam review solutions. And I have put stuff like that on the exam. Usually shorter, easier versions than this particular circuit. More like example 1, or I don't know what I'm going to do. Where am I going? PowerPoint. Let's do that. Where's me out even? We did that. We did that. We did that. And we are done. Any questions? Homework's due. Homework's due for analog on Monday. I will be in my office. Whatchamacallit? What's tomorrow? Thursday. I'll be in my office. What scored it against solitaire? Yeah, I didn't finish the game, unfortunately. I opened that up at the start of my office hours, and I had 280 people emailing me, and I had 380 people panicking about the homework, and I had 490 people panicking about both the homework and the project. So I kicked them out at 3:35. Okay, any other questions? I didn't even get to, yeah, never mind. I didn't get to do a lot today. Mostly helping students. That's what I'm doing about this time of the semester. And then I'm done. Bummer. People who I have missing, let me see. Mark. Fabian, I got you. So Mark's the only one.
Mubarak or Mark?
I said Mark, not Mubarak. Oh. Mark, you're here. Okay. All right. I will see you guys later. Okay. Everybody's leaving.